Hello class, this is Mr. Hasty again. Today we're going to be covering the shell method, which is an alternative to the washer method for finding the volumes of rotational solids. The first thing we're going to do is discuss why we would need an alternative method. The second is to discuss the logic behind the method. And the third is to show a few examples of using the method. So if we look at this purple curve I have down here, this is the sine curve from 0 to pi. Now, if we were to try to rotate this around the y-axis with the equation y equals sine x, we would remember that to rotate something around the y-axis, we want to have it in terms of y. This creates problems. In this particular scenario, sine x does not have what we call a true inverse. The function x equals inverse sine of y has a restricted domain. And if we tried to use that, we would only really be using this part of the function right here, unless we'd miss part of our volume. So our alternative method is that instead of thinking of it in the standard terms that we do and rewriting it in this form, we're going to continue with it in that form, which means we need an alternative method for finding the volume. The standard approach to finding volume is to create circular cross sections that allow us to form the washer approach. The shell method is going to look something like this, where we have these cylindrical shells around the solid being generated. If you look, you can see the y equals sine x curve hidden behind those sections. So if we remember the formula for the area of a cylinder, surface area, it is 2 pi r squared plus 2 pi rh. We've talked about this before. The 2 pi r squared portion references for a standard cylinder the circle at the top and the circle at the bottom, whereas the 2 pi rh refers to the lateral area. The lateral area is going to be the only thing of concern to us in this particular scenario, because there are not full circles at the top or bottom of each of these cylinders. So the area formula we're typically going to use for the shell method is 2 pi rh. It's going to be important to keep in mind as we go through a few examples. So our first example is going to be finding the volume of the solid generated by revolving one arc of a sine curve about the y-axis. This is what I was leading into previously. In this scenario, if I draw our first arc of the sine curve, we should know that it's going to go through at the point 0, 0 and at the point pi 0. This is going to be important for establishing our bounds. Now, how do we get from this area formula to 1 in terms of our variable in question, which is going to be x? So our formula for the area in terms of our variable x, the 2 pi will stay 2 pi. But what is our radius? If we visualize one cylinder right here being rotated around, the distance from here to here, the axis of rotation to that cylinder, would be our radius. Anytime we have a distance from the y-axis to a particular point within a curve, we can refer to that as x. So our radius is just going to be called x. Now, for the height of this particular section is defined by the curve. We could call that y. But we already know that for this curve, y equals sine x. Our height is going to be sine x. So again, our radius is going to be x, and for all of our initial examples, that's going to turn out to be true. And our height is going to be based on the curve. So how do we turn this into a volume? The standard approach that adding up an infinite number of these area sections will result in the volume. So our volume is going to be the integral of that area formula. Now what would our bounds be? X represents the radius. So if we look at the curve again, what's the shortest radius we could have? The shortest radius we would have is 0, right at the beginning. And the longest radius we would have would be pi, all the way at the end. So we do that calculation, and using our standard level of approximation, we get that is 19.739, and I'm assuming we used a calculator here. You could do it other ways. You could do this with integration by parts or tabular integration. And if you want to include units, it would be units cubed, but I just did this on a calculator using my Scikit Calc 7 on a TI model. So that's our first example. All right, let's look at another example. Find the volume of the solid generated when the region bounded by y equals negative x cubed minus 3x squared plus 5x, and the x-axis in the first quadrant is rotated about the y-axis. So first of all, let's get an idea what this curve looks like and where exactly the region we're talking about. I'm going to go to Desmos, and I have a couple graphs here today. So this is the curve we're talking about. If I zoom out a little bit, we can see that it is a normal cubic function, but our question specifically asks about the curve, the x-axis in the first quadrant, which is going to mean the region from 0 to, if we look at it, 1.193 within that curve. And we're rotating around the y-axis. So if I draw a rough sketch of that, it's going to look similar to our sine curve. And this is going to be at 1.193. Now, if we look at this equation, we actually see something a little bit more in line with what I was talking about earlier. How would you go about solving that for x and getting x by itself? The algebra required to do that, on top of this not having a proper inverse, it could be modeled with maybe specific curves, but it's very, very tricky. So another method is a better approach than our standard washer method. So if we visualize our cylinder, we could pick any point. Our area is going to be 2 pi RH. So our area in terms of x is 2 pi. Again, the distance from the axis to any point of contact we can call x. And our height at that point would be defined by the curve. So the height there would be defined by the curve negative x cubed minus 3x squared plus 5x. And that means our volume would be the integral of that. Dx, of course. Now, our bounds, again, the shortest part of the curve is on the origin 0, 0, so we're going to start at 0. And the furthest point of our curve is at 1.193. Now, a lot of times when we work around y, people are like, well, aren't we supposed to use y coordinates for that? But all of our variables are in terms of x, and so we need everything in terms of x coordinates. So now we do the second calc 7 and get approximately 15.198. All right. Last example. Find the volume of the solid generated by taking the region bounded by y equals x minus 5 quantity squared and y equals 4 and rotating about the y-axis. So let's go to Desmos and get an idea what this looks like. Put the two curves on there. I'm going to move this over. Zoom out a little bit. So we can see that parabola and horizontal line have a clearly defined bounded region. I'm going to do a quick sketch of that after I find their intercepts. 3, 4, and 7, 4. Very nice numbers to be working with. So let's go ahead and sketch this. Now there are some things that are tricky in this one, in this particular example. Given that our given that our region is inside and separated from the axis, we've got a little thinking to do. So if I draw this right here as my height of my cylinder being moved around, and I think about, well, that's going to be all the way over here. It's going to be really far away. We have a pretty big cylinder to work with there. So how are we going to change this up? So our area formula is still 2 pi RH. Now, our radius is going to be from the axis of rotation to the edge of our cylinder. We're still going to call that x. Now, what's going to change, because it feels like something should be different because we're not real close to the axis of rotation, what's going to change there is our bounds, and we'll talk about that in a second. What would the height be? So in this case, our height is not just one curve. The height of the cylinder is not just the distance to 4. If we look at our curve, if I want to know this distance right here, that's our height, I need to take the top curve minus the bottom curve, or in this case, 4 minus the quantity x minus 5, quantity squared. So our volume is the integral of that. With respect to x. Now bounds. Because our curves intersect first at x equals 3 and later intersect again at x equals 7, our bounds are going to be 3 to 7. And this is why we didn't need to change this x. The first radius we're going to talk about is not going to be until 3 because that's our low bound. And the next the final radius we would have would be where they intersect again at 7. So we don't need to modify that x. The bounds do the work for us. When we use our calculator, we get 335.103, which seems large. But if we think about this compared to the other ones, the first thing I'd like to notice that this cylinder could have a height as high as 4. These cylinders could. And their distances, because they're so far away from the x-axis, from the y-axis, they're going to cover a lot of ground as they rotate around. If we go back and look at a previous example shortly, this graph, it never gets that far away from the y-axis. It only gets up to 1.193 units away, making for a shorter journey around, and thus less total volume. So that's been our introduction to the shell method. I'm going to put out a video later discussing how to choose which method, shell or washer, and also how to rotate around things that are not just the X and Y axis. So try to keep working on your 7.3 homework, and I hope things are going well for you guys. See you next time.